good you really know your basics, the fundamentals, and you practice them. There are three things, or the three core concepts or steps involved in method of sections that you should really not memorize them, but stick to them. Of all those 7 steps, right, it comes down to these 3 important steps, right? You would cut the member, meaning the member that you want to find its force, and as few as possible other members. So that's the first thing that you need to really be careful about, okay? Do not cut too many members, or make sure that you identify zero force members. That's why, in fact, identifying zero force members is important, because if you don't, you may not see that you have only 3 members to cut. You may think that you cannot find only 3 members, or end up with only 3 unknowns. So that's the first important step, right? When you do that, okay, after you perform that cut, okay, you would basically draw Freebody diagram of a section with the least number of unknowns. Because when you cut the truss into 2 pieces, you have 2 pieces, each has, of course, certain number of unknowns, especially the part that has the supports, obviously would give you more unknowns, right? So don't go by the fact that you automatically find the external support reactions or add more work for yourself, right? Just cut it, look at which piece has the least number of unknowns. Once you've done that, then the third step, I would write it like this. Now use equations of equilibrium wisely. What do I mean by that? Okay. First of all, if you, most of the time, you have only 3 unknowns, right? And you've been asked to find one of those unknowns, right? At least one at a time. So don't just write those in any order. Try to write these equations, or choose the one that would eliminate the unknowns that you do not need to find. Do not create extra work for yourself. If you've been asked to find only one member force, you only have 3 unknowns, find the point of intersection of the other 2 unknowns, make the summation of moment about that point, so you can get rid of those and you only find 1 unknown. Or write summation of forces maybe along the y-axis, maybe that's the equation, that will only give you 1 unknown. So that's what I mean, you use it wisely. Also, even here, when you're cutting these members, it may happen that you may have the same number of unknowns, not just by performing a single cut, but maybe there are 2 cuts possible, and each of them would give you the same number of unknowns. In that case, you perform the cut in such a way that you reduce the number of cuts. In other words, you're asked to find 3 unknowns, okay? For each unknown, you need to perform a section. But it may happen that you can visualize and discover that, oh, if I do use this section, although I cut 2 members with that unknown in that by doing that section, but still I can use the same equations of equilibrium or the same free body diagram to find both of them. So let me, through a simple example, further demonstrate what I mean. And this is a problem was actually brought to my attention by someone in the other section. I thought it's a simple problem, but it's a good example that to show the importance of these concepts. So this was, if I'm not mistaken, this was the problem. It was actually a problem in your book. So this is the problem like this, and I think it was labeled like this: A, B, C, D, E, F, G, H, I. So this truss is loaded like this, okay? And the problem asks you to find this member force and this member force, okay? So obviously you start with the first one and you want to cut that member and as few members as possible, right? So you can see that in this case, there are two possibilities. One is this: you're cutting only 3 members. One of them is the unknown, right, that you want to find. Also, you can cut this way. Again, the same number of unknowns. So in this case, I would consider this section, although both of them give me 3 unknowns, but I consider this one because with the same cut, I can find both of the unknowns, okay? Whereas if I consider this one, I need a free body diagram to find this, then I have to perform another cut because I have to cut this member, so I have 2 free body diagrams to draw. So be wise. So with that said, this is what I'm going to do. I will cut this, okay? Now, consider the free body diagram that gives you the least number of unknowns, right? How many unknowns you have here? Okay. Let's say if I draw both free body diagrams, okay? How many unknowns do I have? In this one, I have 1, 2, 3, but with this one, I have 1, 2, 3, 4, 5, 6, or 5 or 6, right? So obviously, I'm going to consider this one, okay? So I get rid of this. I don't want it, I don't need it. So that was step 2. Now I'm going to use equations of equilibrium to find the unknowns. And the unknowns are, okay, force of C, E, and the force in, what was it, E, F. These are the forces that I've been asked to find. So this one first, and this one second. Again, consider using the equations of equilibrium wisely. If you want to find this unknown, just try to see if you can use equations of equilibrium in such a way that you only have one unknown, and you want to find that one unknown. How do I do that here? Is it possible that I would use only one equation of equilibrium to find that one unknown? Anybody? Any suggestion? Summation of moments about E. If you take summation of moments about E, you basically eliminate these two. I want to find this one and this one.
I.
If I take summation of moments about I, you get rid of this one and this one, you find this one. I want to find this one first. You see it. You can see it.
Intersection between
Which one?
The vertical one, FEF, and IH.
Let me see what you. Which
Going now
one?
about F.
Beautiful, yes. Right? This is F. How about taking summation of moments about F? You immediately eliminate these two unknowns that you do not want. So you just take summation of moments about F is equal to 0, right? So that will give you LCE, generates a moment that is positive. By the way, this was 3 meters, you need those, right? And this was given in the problem as 2.5 meters. So you have FC times 2.5 meters, okay, minus 10 times 3 minus 10 times 6 is equal to 0. So that's 90 divided by 2.5. FCE would be 36 kips. Okay? Came out to be positive. That means the assumed direction is correct. Force is moving away from the joint. That means that member is in tension or compression. Tension. Okay? So that's that. Right? Now I want to find this one. And again, I only want to use one equation of equilibrium. I always want to find the minimum effort, use a minimum effort to find those unknowns. So what is the best way of doing that? Now, what would be the best equation to use of the 2 equations that I have left?
Moment I.
Moment about I. That is correct. If you take summation of moments about I equal to 0, right? You don't need to worry about this force, or of course, although we had that force, but still, I don't need to worry about it, right? On the other hand, if I was asked to find this unknown, summation of forces about X would be the wise choice. But anyway, take summation of moments about I, right? So this and this don't generate a moment, it's only this one, and that would be F of EF times 6, negative, right? This one would be also negative. I'm sorry, this one would be positive, and this one would be positive. So it would be plus 10 times 6, plus this one, 10 times 3, equal to 0. So F of 90 divided by 15. So that will give me FEF, 15 kips, came out to be positive. That means the assumed direction is correct. Force going towards the joint, so the corresponding member is in compression. That's it. Okay, so just remember these 3 essential guiding principles. I'm not saying that necessarily you have to follow these steps, but it makes your life easier. You can, for instance here, you could just simply start summation of moment forces along X or Y. That's okay. You have 3 equations and 3 unknowns. You can solve them any way you want. But just going this way, at one, you only find one unknown at a time, so it makes your life easier. Okay? Any other questions? So we've talked about trusses, method of joints, right? 7 steps. Remember, set up your XY coordinates. Then you consider the 0 force members. You get rid of them. Step 2. Then you go to the joint with the least number of members coming to that. Step 3. Draw its free body diagram, which is the step 4, and solve for as many unknowns as you can, right? Then step 5, go to the next joint and with the minimum number of unknowns, and do the same. Next step is, if you need to, find the support reaction forces. If you don't have to, you don't have to, but if you need, you end up with a piece, for instance, that requires that you do that. And then last step is basically you continue this until you're done and verify your results by using the equilibrium of the last joint, okay, that you haven't used. And method of section, we saw that the 3 essential steps of this, but basically you also set up your coordinate system, get rid of 0 force members, which is actually very important, because that may reduce the number of unknowns that you're looking for, or number of steps, and then follow these 3 essential steps and continue the same. So that's trusses, not that, okay? And with that said, let's see where we are. Any questions? Where are we in the course? We said statics was about forces and the action of forces on structures. So for the past couple of weeks, we've been looking at the action of forces on the structures, which we call them what? Rigid body equilibrium. And in rigid body equilibrium, we basically did 2 things. We learned how to find support reaction forces, that is, forces acting on the structure externally. If you want to design those support mechanisms, you need to know them. But then, if you want to design the structure and different pieces, you also need to find internal forces, or forces at the connections, right? And, of course, in this case, we looked at 2 types of structures, frames and machines, and trusses. In all these discussions that we have, right, it was mainly based on one of the key or pivotal concept was the 3rd law of mechanics, law of action and reaction. When you take 2 pieces apart, there's always the same force at the point of connection that exists on the 2 pieces equaling magnitude opposite in direction, okay? In all of the studies that we did, right, we made one big assumption. And this was the assumption, that of all the types of connections or the supports that hold the structure in place, if 2 bodies are in contact in such a way that they can move or slide with respect to each other, right, the type of joint or mechanism that we assumed or we modeled, in fact, that existed, we modeled that this way. If there was the possibility of relative motion, linear motion between these 2, or translational motion, we are not talking about rotational motion, that's a different topic in itself. Or you have something like this, right? 2 bodies can slide with respect to each other. We assume that the only force that exists is a force that is perpendicular to the potential direction of motion. So now we want to introduce not a new concept in a way. Static is what we have discussed so far. Nothing is new. We just want to, how should I say, expand our knowledge about forces a little bit. We have made an assumption that, in fact, it was not a good assumption, so we want to show you that, in fact, this assumption is not 100% true, and if it is not true, then what happens? So in other words, what we've done so far, what we've discussed so far, all the concept we have introduced, that's about it. That's all we needed to know in the statics, which is what? Free body diagrams and equations of motion, equations of equilibrium. The tools that we have to solve any static problem. Now, we just want to violate one assumption that we made here and to show you that in reality there is no such a thing. So we have actually ignored the presence of a force, and please consider that in those free body diagrams that we've been talking about so far. That's all we want to do. So that's the topic of friction. So what is friction? Okay, let's simplify that. You've seen that in physics, So we're not gonna, of course, discuss it very in depth, very simple sort of approach to friction problem, but what is it? So the purpose of studying friction in statics is that you just want to learn a little bit more about the case that you have, in fact, the possibility of motion between those two pieces, and find that additional force that we have so far ignored or assumed does not exist. Okay? You remember from physics, okay, when two bodies are in contact, and this is how it was presented in physics, right? Let's say you have an object residing on a surface, and you try to basically move that object by exerting a force that will increase, right? You do know that, obviously, based on everything we've discussed so far, since these two can slide with respect to each other, you have a force, which we call that sort of the normal force, okay? But knowing that, what we had told you is not true anymore. In other words, as you're trying to pull this object, it is not immediately going to slide, but something is resisting it. That resistance is a force that actually a very complex force. It is not as simple as you can think of. In reality, that force is actually a distributed force, okay, in both directions. But we make the assumption that there are actually two forces here. One is what we have discussed so far, that vertical force, which we call that N. But as you try to move this object, another force actually develops between this and the ground that is residing on, which we call that force of friction. Okay? So this is called friction force. This force of friction, which we have so far ignored or assumed did not exist, is a very complex force. But in statics and in most engineering analysis, in fact, we simplify this. What do we mean by simplifying that? We assume this is what this force is all about. Okay? First of all, this force is, okay, a function of the material that this surface is made of, or these two are made of. Okay, between the two, or the connection between the two. Okay, each material in the world has certain properties when it comes to resisting this rubbing motion. We call that coefficient of friction. For instance, coefficient of rubber is larger than the coefficient of friction for wood or for steel. Okay? So when I say it's a function of materials, meaning there's a function of this coefficient of friction. Number two, okay, as this force is increasing, this friction force changes. So this friction force is a variable, is not actually a constant. And the way it varies is like this. If this force is increasing, and this is that friction force, as you increase that force, we make the assumption that up to certain level, which we call that F sub S, this friction force stays as a linear function. And at this point, which is its maximum value, this F sub S, is that coefficient of friction times that normal force. That coefficient of friction at that point, okay, is based on the assumption that this has not moved yet. Okay? As you further increase now, beyond this point, this force, this actually drops, and then that you do not need to, this force stays constant and does not increase, or we assume it does not increase, and the value of that force, which we call that kinetic friction force, is equal to a coefficient times n, which we call that kinetic or dynamic coefficient of friction, kinetic coefficient of friction. In other words, as this force increases, right, okay, this friction force beyond this point stays the same. Okay. That is the assumption we made, or we didn't make. A gentleman by the name Coulomb actually came up with this idea many years ago, that to make us, basically, to enable us to be able to solve problems in statics or dynamics, as you will see later, with a simple sort of approach, which is a very reasonable assumption that this friction force has a maximum value up until that maximum value is linearly related to this, and beyond that, it stays constant. So now talking about the statics problem in, friction problems in statics, there are basically three situations that you encounter dealing with friction force. Okay? Either the force that is applied, okay, is greater than F sub S. Okay? In other words, if this is the force, whatever the projection is, okay, let me call this P like this to make it more meaningful, okay? A force that is resisting that motion, which was this, F of F, right? We said its maximum value is mu S times N. If this P is greater than that force, which is resisting the motion, obviously the object is moving. And motion is definitely going to occur. This is not of our interest. We're dealing in statics with equilibrium, right? We don't care about motion. So there are two other cases, okay? The other two cases are, you are told that definitely we know this P is less than the possible maximum friction force that can develop. The problem statement is such that it either gives you that information explicitly or implicitly. So, yes?
Is it less than or equal to?
Less than or equal to, yes. Okay. So, if you're given that information, okay, in the problem, you then know, okay, that the object is not moving. No motion for sure, right? Or you have static equilibrium, okay? So you know that F of S is mu times N. So this force of friction is known with respect to other variables that you could find from the Freebody diagram. In other words, all you have to do, you draw exactly the same Freebody diagram that you had before, just add a force along the surface of potential motion, right, in the opposite direction that motion may occur, and we know the value of that force is not a new variable, is not a new unknown. So the problem has no new unknowns, same number of equations, you solve that, right? So this is case number 2. Case number 3, okay, is we do not know, okay? We do not know if this is equal to F of S or not. We don't know. We know that we have friction. We don't know if it's gonna move in certain direction due to the applied forces that are acting on the structure or not along that surface of contact, okay? So in this case, we need to find that friction force and treat that as a new variable, as an unknown, additional unknown, okay? So we need to find that. Once you find that, okay, obviously, if this f of f is less than or equal to f of s, right, what happens? You know, right? So if it is equal, that is what?
It's not gonna move, is it?
It's not gonna move, right? So that means we have equilibrium. Right? So treat the problem exactly as you did before, right? You have the free body diagram, you find that, right? And if is greater than that or exceeds that, okay, then it's gonna move, so we don't have a static problem anymore, right? So in other words, in this case, you use the same free body diagram with this friction force as an unknown, and you just simply find it. And then verify if it is less than mu sub n or greater than that. And you then decide whether it's gonna move or not. So that's all there is to it in the friction problems in statics. So we have only these two cases. So we are going to look at sets of problems in both cases so that we can really understand how to solve the problem and understand these two cases. Yes?
When solving for friction, will we need to differentiate between static and kinematic, or are we only dealing with static?
You know, when you're talking about this case, because if this is the case, you know that we're dealing with only static coefficient of friction, and that's it. So that's the assumption. But here we don't know. We just assume we need to find the friction force and find out what it is. Is it mu n or not? That's it. So to decide whether it's moving or it's not moving. So let's, the next couple of sessions that we have, we will just devote that to solve problems of both types, so you become master at friction as well, okay? But the good news is we're not dealing with anything new. Just treat the problem as we did before, whether it's a frame problem, whether any kind of rigid body equilibrium problem, you just treat it exactly the same as before. You just have an additional force, that's it. So let me start with a simple problem first of the first type, okay? So I'm going to look at case 1, okay, that we know friction exists, but we do know there's no motion. And as I said, this information, whether that motion does not, in other words, if body is not going to move, may be stated explicitly or implicitly. And that's in fact the case in this problem. So it's a wonderful ladder problem that is the most common problem in almost any book on friction, topic of friction. So this was a problem. In fact, this was a final exam problem. You have a ladder which is 12 foot long, and a crazy man that he just wants to defy all the rules. He wants to, instead of listening to the label, watching and reading the label on the ladder that says do not go beyond this step, he wants to go all the way to the top, right? So he wants to know at what angle he should lay this ladder against that wall that it does not slide on this floor. So this floor has friction. This wall has no friction, okay? That's it. So let me label this as A and B. So we just want to find the minimum angle, I'm sorry, the maximum angle that should set this against this wall. In other words, anything larger than that would cause the sliding of this ladder against this floor. So, as you can see, nothing new. You just draw a free-body diagram based on the information that you have, right? And what is a free-body diagram? All that you have to add is what? Here, first of all, let's put the externally applied forces, right? So you have the weight of 30 pounds given at 30 pounds. Okay? As far as the supporting actions, there is no friction here, so you have a force of NB, right? Because it can slide against that wall, so it's like a roller. But here you have friction. Force of friction is always in the opposite direction of the potential motion, right? So if this is going to slide, would it slide this way? So force of friction would be that way, right? And of course we have that vertical force. So that's the free body diagram, that's it. So the first step is not going to change. You draw the free body diagram, so that's the first step. And then second step, just use equations of equilibrium to find the unknown. So this first type of problem is very, very simple. You just, nothing, literally nothing new, right? So how do you do that? Okay, you have three unknowns, right? Because you know that if this is not moving, you assume that this is the maximum friction force, which is mu sub s times NA. And by the way, mu sub s is given as 0.5. Okay? So it's not a new force, I mean, it's not an additional force, it's related to NA. So based on that, this is alpha. So this distance then would be 12 cosine alpha. This would be, okay, 12 sine alpha, right? Okay. So start with the equations of equilibrium. Always remember, use the equation of equilibrium first. That can eliminate as many unknowns as you can. That concept still holds, right? And I can see that here, the easiest one would be just starting with summation of forces along y equal to 0 because I have only one unknown. So n sub a minus 180 pounds minus 30 pounds equal to 0. So n sub a is 210 pounds. Okay? Then the next easiest one would be obviously summation of force. Given this, that we know friction force is 0.5 times NA, right? So you just write summation of forces along x is equal to 0, so you have 0.5, and A is, or I should write it that way, minus NB, which is equal to 0. You have NA 210, so NB would be 105 pounds. Okay? So you have two unknowns, NA, NB, and alpha, right? So, and one more equation. That one more equation would be summation of moments that you can either think about this point, right? Or any point for that matter, because you have both unknowns. So I'll just take it about point A. So you have NB, which I write the value actually, 105 times this distance, 12 cosine alpha, minus 180 times 12 sine alpha, then minus 30 times 6 sine alpha is equal to 0. I would divide everything by 6 here. Okay. Actually, I can divide by 12. 12, 12. So this is 15, right? So and then I would divide both sides by cosine alpha, right? So you will have minus 180, right? Minus 15 times tangent alpha, okay, is equal to, is equal to 105. Okay, if you solve this, you get, I believe, tangent alpha is equal to 7 over 13, which gives you alpha 28.3. So you need to lay this ladder at an angle of 28.3 or less than that, so that you would avoid the slippage. Of course, that's quite a steep slope, so wish him luck as he's going up the ladder. So easy, right? So that's the first type of friction problem. So I'm going to stop there because I don't think we have time to go over another problem, but we are off to a good start. So I'm going to do more problems on Wednesday.